So question 7 out of 11.1. The author drilled a hole in a die and filled it with a lead weight, then proceeded to roll it 200 times. Here are the observed frequencies for the outcomes of 1, 2, 3, 4, 5, 6 respectively. Again, these numbers are just categories for the die there. So they got 27 ones, 31 twos, 42 threes, 40 fours, 28 fives, and 32 sixes. Use a 0.05 significance level to test the claim that the outcomes are not equally likely. Does it appear that the loaded die behaves differently than a fair die? So that's our interpretation question that we'll answer after we've done everything else. And our claim here, test the claim that the outcomes are not equally likely. So claim is that the proportions not equally likely. And if we were to go ahead with the opposite or negation of that, that would be that the proportions are equally likely. So when we come over here to write our hypothesis statement, null and alternate, those are just labels. Our null hypothesis has, in this case, it's what we see here, the proportions are equally likely. All the proportions would be the same. So we could say that the proportions of 1 equal the proportions of 2s equals the proportions of 3s equals the proportions of 4s equals proportions of 5 equals the proportions of 6. Or we could just write in English, all population proportions are the same. And then the opposite of that would be at least one proportion is different. Alternately, we could write not all the proportions are equal. Just like before, put the R and the S. Which one of these matches up with the claim? Well, the claim is the proportions are not equally likely. That's saying at least one of them is different. It's the alternate that represents the claim here. Our significance level is alpha here, 0.05. What I have in the instructions right now, I'm still asking you to identify the tail of the test, mostly because I want you to keep saying that this is a right tail test, and you go through it a couple times, right tail, right tail, right tail, then it sticks in your head that this is always going to be a right tail test. Eventually what I'll do, and you'll see me do this, is B and C will eventually be combined, where it's just identify alpha and then immediately go ahead and use it to write our rule of rejection, which is reject null hypothesis if p-value less than or equal to our alpha level there, 0.05. So at this point, we're ready to go to statdisk and enter in. This time we only have to enter in our observed frequencies, and that's because our null hypothesis is that all the proportions are the same. Okay, just wanted to make sure I didn't didn't lose these numbers when I switched screens here. So let's head on over to statdisk. And what we have to do is put in our frequencies. So we had 27, 31, 42, 40, 28, 32, and then always take a moment or two to double check that you type things in correctly, because data entry errors are expensive mistakes in statistics in the real world, so they're expensive mistakes in a statistics class. So analysis, goodness of fit, and our null hypothesis had all the proportions equal to each other. That's why it's equal expected frequencies. Our significance level was 0.05. Our data is in column 1. We can hit evaluate. You can also go ahead and hit plot. And in our plot there, we see that our test statistic blue is not off in that upper tail. And let's just take this data back to our screen here. So our chi-squared here is 5.860 and p-value 0.3201. So is 32% less than 5%? No, it is not. So we fail to reject the null hypothesis. And when we fail to reject the null hypothesis, we have insufficient evidence to do whatever we're going to do. Well, up here we noted it was the yes, so support. Claim that, and then we just bring it back to exactly what the claim was. The outcomes are not equally likely. So reading that all together, we have insufficient evidence to support the claim that the outcomes are not equally likely. We didn't reject the null hypothesis, and the null hypothesis said that the proportions were all the same. Well, the proportions of all the same is what we'd expect of a fair die. Unless we had enough evidence to the contrary, we went under the assumption that we were working with a fair die. And we couldn't reject that claim. So when it asks us, does it appear that the loaded die behaves differently than a fair die? Our answer here is no. There wasn't enough of a difference. The results that we got were consistent enough with what we'd expect to get if our die was fair and all the proportions were equal. Now, he rolled it 200 times. Would that change maybe if he rolled it 1,000 times, if he rolled it more times? It might. But when we go through and do this, we work with the data that we have, we work with the sample that was taken, and our sample here says that the results that we got were consistent enough with what we'd expect from a population generated by a fair die. Mark, anything?